السلام عليكم يا جماعة. ماشي، بعتذر عن التأخير، ما كنتش لاقي اللينك بتاع الزوم.
وعليكم السلام ورحمة الله. أهلا يا دكتور، عظم الله أجركم.
شكر الله سعيد، جزاك الله خير.
عليكم السلام دكتور.
طيب، نبتدي إن شاء الله عشان ما نتأخرش. last time we ran some code together, but we didn't get to finish the entire notebook. So based on a quick vote here, did you guys end up running the notebook yourself? Did you have any issues? Would you like us to go over the rest, or was it fine? Shall we move on to other things to discuss today?
The truth is, I haven't tried to, but I vote to move on.
Okay, that's one vote. Anyone else interested in giving their vote? Okay, let's then just share my screen. Sec. All right, so um, today we have an interesting topic for discussion. So let's just start by introducing what I call a curse of complexity. We have seen data before. This is just some distribution from like a linear relationship between x and y with some added noise. Then we can kind of see that we have two routes here. Now that we've hopefully understood how neural networks work, and that we could essentially design a model to include as many hidden layers and as many hidden units as we want. We can at times get tempted to do something like this. Like, for example, if the data is seemingly linear, but it has a little bit of noise, we can keep adding hidden layers and more parameters to the model. Actually, the model fit the data uniquely, assuming that the data comes from like a linear distribution, which is this linear relation between model with only two parameters. We can get like this also straight line, which is more or less very close to the actual true function of the data. But we can also build the model with 526 parameters, and this seem, bigger number compared to two parameters. But in the universe of deep learning, 500 parameters is a really tiny model, not even small. It's a tiny model. And I mean, you can kind of tell that the loss function, which is the MSE, directly what we use with linear functions, you can see that as we get complex and as we try and break our straight line into nonlinear regions, we actually do reduce the we do reduce fitting the data better. But then the question happens, or the question is, what happens when we get a fresh data set? So this is also a linear data set, but it's a different data set. So the noise in the data, the the true function underlying the data is still the same. So you can see like the same dotted straight line is the same, but the actual data points are different. And because the data points essentially reflect a little bit of noise around the true function, you can kind of see that if we are to use that simple model that we developed with two parameters, we get like a slightly higher loss from the other data set, which is to be expected. Usually the test loss is higher than the train loss because the train loss is really the data that the model has seen and the data that has helped the model to learn. So it should be as low as possible, as far as the model performance goes. But then once you go and apply that very complex model that we developed that had a really low training loss, you see that now we're getting a much higher loss when it comes to this complex model. And essentially, what this is like, what this phenomenon is called, it's called overfitting. What we have done essentially is instead of understanding or instead of teaching the model the underlying pattern in the data, which in this case is a very simple pattern, it's a linear relationship. We've actually taught the model to learn all the noisy bits in the data points that were in the training data itself. So we're not really learning the pattern, we're just learning the noise. And then when we get a new data set that has obviously a different level of noise, so the data is noisy in different ways, now this is a very bad model. The performance degrades way too much. So if we are to just plot like this is the simple model, and we're just plotting the loss value between the train set and the test set in both cases, this difference between the test and the train, we call this the generalization. The generalization gap. And obviously you can see that with the complex model, there's a huge gap between your training loss and your test loss. And this is an obvious sign that you're overfitting the model. Any questions there? I think we might have mentioned this quickly in some of the previous lectures, but we're just trying to formalize this. Okay. Other extreme. So that was the curse of complexity, and that's the pearl of simplicity now. So now um, this should not be an invitation to oversimplify things, right? So for example, this is like the other end of the spectrum that you have. Here you have a parabola function. So this is obviously a nonlinear function. And we are trying to, again, use a neural network that is underfitting. In this case, the neural network has also two parameters. And I think I even switched off the ReLU function, so it doesn't really break it. It doesn't have nonlinearity in it. So you see that it's trying to fit a straight line through data that is obviously nonlinear. And we're getting like even the training loss itself is quite high. And in here, we're trying to do like a quote unquote correct fit. And this again is you can do like some parameter sweep and see like what would be like again a complex and what would be a correct and what would be an underfitting. But you get the idea. This looks fairly decent, given that the actual true function is a parabola here, and you see the data is like just some noise around it. So you see like the training loss here is way less because this is a proper fitting model. The same idea here applies once we go and switch the data set that we use to a different data set. We see that the underfitting model still does bad, like it did bad on the training data. So it's obviously going to do bad also on the test data. And the correct model is like test law is kind of like but fairly real, right? It's fairly reasonable to say that this model is actually fitting the data properly and not else. So these are kind of like the two ends of the spectrum that you have a model where you're just overfitting, you're going like really over with like your parameter, whereas the underlying function is actually quite simple. And this is the case. You actually have like linear It's a non-linear function. Fit a linear model too, which is obviously
to
دكتور مريم حضرتك هنا. Okay, we're back. Recording is back. Okay. Okay. So I was saying, yeah, these are the two ends of the spectrum, um, where you have like a situation where, um, sorry, just I'm trying to see my Zoom screen. Um, where's the chat? Oops. Okay, I can't see the chat, so if anyone is typing something in the chat, please just raise your hand. Um, Sorry. So I was saying these are the two ends of the spectrum. Okay, sorry. Never mind. I got the chat. Yeah, these are the two ends of the spectrum, the overfitting and the underfitting. So I think a natural question here would be, how do I know beforehand? Like these were pretty simple models that we can visualize and we can see the train and the test laws. How can we know whether I am overfitting or underfitting a model? Like if I'm working on data, I'm obviously like I will have some information about the data. I will have some like I would understand the data features, do some, standardization, normalization, that kind of stuff. But how do I know that the model I have picked is actually not overfitting and not underfitting? Any thoughts how to do this in a real world situation?
I would guess using two test sets, training sets. One to just create the function, and the other to test
Parameters. It uses whatever parameters it had learned throughout the training, and it just uses the input and produces an output. It's not
yeah.
really learning anything, right? And then
No.
there is the back propagation. Then it computes a loss. The loss is what? The loss is we
Mhm.
take the output that the model produced, and then we compare this to the ground truth. We call it the ground truth, which are the labels we provide, the labels attached to the data um, we just put through the model. And then we use a process called backpropagation. In backpropagation, we essentially use start from the end of the network and try to walk our way back in the network, updating the weights to try and improve the loss, to try and go towards the minimum of the function, right?
Right.
So in the training data essentially goes through the forward feed and then the back propagation. In the test data, all we do is we take the model in its final state, in the final state where we have the final weights and biases and all the parameters, and we just compute the output. And then we calculate the loss on the output. So we still need the labels to be able to calculate the loss. Okay? Now this is the idea. So there is a process. There is a process that is called cross-validation, and I think I like to think about it in the entire training process in this analogy of you have practice or homework, and you have quizzes, and then you have the final exam. So the idea is, I'll explain what this means. The idea is, in order for us to know whether we're overfitting or underfitting, we're trying to compare the model's performance on data it has seen to its performance on data it has not seen. This was the example I just showed. Trained on a data set, and then once we try to apply the model to a fresh set of data that it hasn't seen at all, then we captured in the training data rather than the underlying pattern or the underlying mathematical function that describes the data, regardless of that level of the noise. So that's really like our thermometer here and understanding whether or not we are over or under fitting. And then in order to do this in a very systematic way, as we're training the model, we use a process called cross-validation. So the cross-validation essentially entails that if you have this, like this is your entire data, you're gonna take all the data and you're gonna break it up into three different parts. One part is gonna be the training data. This is the data where you use to train the model, meaning this is the data that passes through the entire network, meaning it goes into forward feed and it goes into back propagation and updates the parameters every time until it converges or until it reaches the number of epochs we set it to. But this is how this data is being treated in the network. And then you have a set of data called the development set or the validation set. And the purpose of the development set or the validation set, which so in that analogy here, the training set would be like this is your practice or this is your homework as you're learning something new. So when you're doing like your homework or like your practice questions, you're allowed to ask questions. You make mistakes, you go back to the teacher, they fix, your mistakes, and then you go back, you study, and then you do another, maybe sheet, another assignment, whatever. So you're practicing, and then you keep on you keep on repeating that process until you eventually learn the concept. The dev set or the validation set is kind of like a quiz. So this now is like you've studied a chunk, maybe one or two chapters, and now you're kind of trying to figure out like how much you've learned, whether you're learning from the assignments and the practice questions and the homework really well or not. So you take like a small quiz as like a test to see. And if you do well on the test, then it means that your study approach is doing well and the homeworks are really covering all the topics that you're supposed to study. But if you do bad, then you go and you modify the approach. You go and modify how you're learning. You go and modify the kinds of exercises you practice or you do homework on. In the language of the model, or now like going back to deep learning, this means that when you perform bad in the development set or on the validation set, you're basically trying to tune the parameters of the model. So maybe the validation set, like maybe we see the same pattern here. Like if this was your training data, so like this example here, and this was your validation data. When you go and apply the model to the validation data and you see that your loss is really, really high, it means that you're overfitting the model. So then you go back and you tweak the parameters of the model and say, oh, hey, maybe I have way too many parameters. I need to actually dial it down. I need to reduce the number of hidden layers that I have. It could be other things that you're trying to modify that, for example, would be the learning rate. So maybe the model is not converging. Maybe you want to change the learning rate. It could be something like when we talk about regularization, it could be something like the dropout, for example. So the purpose again of this development, the development or the dev set or validation set, these are all names for the same thing. The problem is after you have finished your training, then you go and test using this validation set. And if the validation set is doing well, then you kind of have an idea that the model parameters is working well. And if not, then you need to change some things about your model. So the
Is it
important
like
thing,
a test on the training set?
sorry?
Is it like a test on the training set?
No, this has nothing to do with the training data. So like remember this blue box, this is our data. We're dividing the data into three different parts. This, like, if the model is training, it doesn't see any of the development data or the test data. This is completely masked from the model as it's training. The development set or the validation set and the test set, so these like green and orange boxes, these are only data that we could put into the model and just calculate the output. So these are like only the feed forward part of the network. These are never used to update the parameters of the model.
So it's like a test to
Yes.
modify the model. Yes.
So that's a good way to put it. So it's a test. It's a kind of test set that we use to tune the hyperparameters. Can someone tell me what hyperparameters are and how they're different from a parameter?
I think hyperparameters which we can modify or update.
So like is weight our weights, for example, our weights and biases hyperparameters?
Uh, no, weights
Why
and
not?
biases are parameters, while learning rate, I think it's a hyperparameter.
So what's the difference? What makes this a parameter versus a hyperparameter?
Parameter, it can be modified by updating it through backpropagation,
Yes.
while
So, mhm.
learning rate, I think we can't modify it this way.
Okay, so yeah, you're really close. So the key thing, just to make the distinction, parameters are things that the model learns as it's training. So anything that the model learns in training, it's called a parameter. Anything that we choose to do, which includes starting from the architecture of the model. So the model can't really learn whether it wants to have 64 hidden units or 1,000 hidden units, right? It cannot really decide what the learning rate is. It cannot decide what optimizer we use. Do we use stochastic gradient descent, or some other algorithm like atoms or whatever, right? So these are choices that we, as we design the neural network, we make. These are the choices we make. But there's nothing that like we obviously we have some theoretical references on how to make choices, but there's a lot of trial and error in picking these hyperparameters. We can have one model for one problem and think that this architecture is going to work well for a different problem, and then we go and apply it and we see that it doesn't really work well. So we have to go back and make changes to these hyperparameters and then train the model again. The thing here to remember is the development set and or the validation set, it never goes into back propagation. So it never really updates the weights and the biases of the model. This is kind of like exactly think of it as the quiz. You cannot really in the quiz, you cannot go and ask the teacher what is the answer to that question. But you can go and do this in the homework. You can go to your TA and say, I can't really figure this out in this part of the assignment. Can you help me figure this out? But you cannot do the same for the quiz. The quiz is you've already done your learning, you've already studied that part for the quiz, and now it's time to evaluate how well you've learned this part. If you learned well, that's fine. Keep going. Let's go and take the final exam because you don't really need to update anything. If you haven't done well on the quiz, the idea is to go back and see what parts did you not really learn well? What parts can you change? What part how can you modify your, studying strategy or, your kinds of problems that you solve as you prepare for the test, right? So
So
then
is the backpropagation happens after the validation?
no, the back propagation ends in the is like okay, let me just use the analogy again. Can
Okay.
you study when you're doing the quiz?
No.
You can't. So you have
Because
already finished your studying and you're being tested. You're being
yes.
examined, right?
Mm-hmm.
So that's exactly the idea. The development test, the development set or the validation set is only used after you've done your training. After you've done your training,
My
you're trying
idea
to see.
is that I
Yeah.
can modify my knowledge after the test or after the quiz, yeah.
If you haven't done well. So if you haven't done
Yeah.
well, you go back and you change something about the way you studied, then you study again, then you take another quiz.
Yes, I'm talking about that. That I can modify after the validation. I mean,
Yes, after the validation. So
yeah.
but you first finish the training, right? You finish the
Mhm.
studying, and then you go take the test with what you've studied. If you did well on the test, then well, you've learned well. If you did bad on the test, then you go back and you study again. So you repeat the training. But with obviously, you're not going to go and repeat the training the same way
With
that you did it
different
the first time and
parameters.
expect something different, right? You're going to repeat it, but with while changing some things or tweaking something. Hopefully that analogy is clear.
Yeah, okay.
So what about the test set? So we've been talking about the def set and the train set. What about the test set? Where does it come into play?
After the validation, and I'm like being sure that I'm doing well, so we are going to enter the test set or the
Okay,
test
so
case, I mean.
yeah. So the test, I like to say this is your final exam, right? So throughout the
Right.
semester, you have maybe like 3 or 4 quizzes. You use the quizzes as like chances to validate how well you're learning. But then hopefully after you buy the last quiz, hopefully that you got like good grades, your approach is working. Now you're ready to go into the final exam. So there is really no difference between the def set and the test set in terms of like, sorry, the def set and the validation set and the test set in terms of the nature of the data. These are still like usually equal parts of the data. So like let's say like 10% of the data is a def set and another 10% is test set. It should be kind of similar in its nature and everything. But again, this is data that the model has not seen before, similar to the def set. But now, after you've gone through some rounds of training and testing using the train set and the validation set, your test set is kind of like your final exam. Now we're trying to test all the stuff we've learned, like the weights, the biases, the hyperparameters, and everything on some real world data. And this hopefully should give you an idea of how well is the model going to perform on some real world data. Okay? Hopefully that's clear. So that's yeah, that's like the analogy here. So just repeating what I said, the training set, this is like your homework, your practice. The purpose here is we're training the model, so we're learning the parameters. We are learning the weights and the biases in the model. This can be anywhere from 80% to 98% of the data, depending on the size of the data. So because like deep learning really relies on extracting patterns from large amounts of data. You don't really want to waste your data or like hold out your data. Oh, by the way, another name for the def set and the validation set is also a holdout set. So these are like the three names that you might come across in like I don't think there is any other names in any of the books, papers, or whatever you read. It's either going to be def set or development set, validation set, and then holdout set. These all refer to the same thing. So you don't want to really hold out a lot of your data from training because you still want the model to learn from as much data as possible to try and understand the patterns. And then the development set, or again the validation set or the holdout set, this is where you kind of tune your model. So like you're trying to tweak hyperparameters, you're trying to learn like adjust your learning rate, the actual architecture of the model. You're trying to make some choices about like whether you're overfitting, underfitting. Am I using the right optimizer? Do I need to change some of the nonlinear functions that I'm using? Maybe I'm using ReLU and now I need to change to, I don't know, rectified ReLU or whatever. So you're basically making some choices about tuning your model and then training another model so that it learns a new sets of weights and biases with the new hyperparameters that you've tuned. Then you test again using the def set until you kind of improve the model performance. And then once you're kind of satisfied after this multiple times or round of training, then you go into the test set. This is your final exam. This is where you get to, you go into the exam, you've studied, you've practiced, you've done your quizzes, you've done your rounds of Q&A with your TA or whatever, and then now you're ready to go into your final exam and ace it. Okay? So this is how it kind of looks. This is the cross-validation cycle. You train, you use your dev set to validate, you adapt or update your architecture, your model, your hyperparameters. You train again, you test on the dev set. If you like it, fine. If you don't, then you adapt, you update, you train again, and so on. And when you're satisfied with the output of this cycle, then you go and test on a test set. There is a term that in this cycle, there is a term here that they sometimes refer to as a researcher bias. Essentially, because think about it this way, that you have you have some training data and you have some test data, and then you're updating and your model and parameters kind of to improve the performance on that dev set or that validation data set. So in a way, you could fall into the trap of trying to overfitting your model so that it performs well on the dev set. So this is something that is sometimes referred to as a researcher bias because you're biasing your training and choices to enhance the performance on the dev set essentially. So you can be kind of unconsciously biasing your model to where it's just performing well on the dev set. Now, this could be a good or a bad thing depending on your choice of the dev set data. So for instance, if you're training a classifier in images, for example, and you're trying to learn, you're trying to have your classifier identify people from their faces, for example. So you have 100 people, and in the 100 people, you have some twins. And the twins are, some of them are in the trained data, and some of them are in the test data or in the validation data. What do you think the validation here is going to represent? So essentially, the model, if there's pictures of twins, it means that we're essentially um, mixing up the training and the test data. So even though the pictures come from different people, but they look very similar. So the model doesn't really know they're different people. The model is just recognizing their facial features, their eyes, their nose, their I don't know, like the facial features of how a person looks. Um, and obviously the test data, like your design of the test data or what makes the test data or your choice of what to include in the test data is actually making the model cheat. So that's what you would, for example, if you read something about like the design of the train and the test data, you will see people talk about the test data being orthogonal or being uncorrelated to your train data. A similar example would be, for example, if you're trying to, the example we refer to many times, a regression example of predicting house prices based on the neighborhood. So, for example, if you train the model on houses like using features, and your test set is essentially some houses from the same neighborhood, so meaning that the prices are going to be heavily correlated with the prices in the training data, you're not really you're not really generalizing the model because your test data is very correlated or unorthogonal with your trained data. Orthogonal is in math it like means like perpendicular, and when we use it to describe the data, it basically, if you say my data or my test data is orthogonal to my trained data, meaning that it's uncorrelated and vice versa. So I think I talked a lot here, but the key take home messages here is this is your cross validation cycle. This is typically how you would train and iterate through training the model. Be very careful in picking your dev set. Um, be very cautious of not overfitting towards just the performance of the dev set, and make sure that your dev set and the test sets are truly test sets and that they are not correlated to the features you see in the training set. Otherwise, you would essentially be replicating some of the training sets and calling it a test set. And your model is gonna do like really well, and you think that you're learning really, really well, but then you get a new test data or a new data set, and you'll see that the model is breaking down, is really just not producing anything. Any questions?
Yes, concerning the choice of in the dev sets and training sets,
Mhm.
uh, do we include noise or outliers in the dev set especially?
You mean you just yeah, like you introduce some noise to the data, or what do you mean? Do we include noise?
Because you told us that the dev set needs to be chosen carefully and which data comes to it,
Yes.
and is noise included or outliers included in the dev set?
Um, so like it's part of your data set eventually. Like I'm not sure I understand what you mean including noise. So like you have your entire training data, sorry, your entire data set. And from this data set, you divide it into you take 80% as like training and 10% as dev and 10% as test. When you're picking those chunks of the data, you try and not have these either be similar or correlated examples from examples in the trained data. I assume that the level of the noise would be kind of uniform across the data set. And if not, then you would just randomize the data so that some noisy examples fall into the training data and some noisy examples fall into the dev and the test sets.
Are the
But I,
outliers being filtered through the pre-processing?
filtering the
So
outlier is a process you want to do before you feed the data as a whole. Like not like
before
if you have
entering the
training
model,
data, yeah. So if you have your training data and you look at the data, you see that there are some outliers and stuff. You would do this before even splitting the data. So like like it's as bad if you train on an outlier as it is if you evaluate on an outlier, right? So because if you have outliers in the training data, you're trying to basically in the training data you penalize the model for not getting something right. So now if you have an outlier and the outlier is going to have a massive loss value because it's going to be so out of distribution. So like the difference between the predicted value and the ground truth is even though the model is actually learning the pattern, because this is an outlier point, when you go and compute the loss, it's going to be a massive loss. So the model is going to think, oh, I'm doing really bad there. I need to improve. So this could actually go in the opposite direction of optimizing the minimum. So the outlier, like quote unquote, an outlier is going to hurt you in both ways. So like the filtration of outlier of like what we call out of distribution data points, you would typically do this in a data cleanup before even dividing the data into train validation and test set. But you don't try and introduce noise or outliers as like let's test how the model works because I mean this is well, unfair to the model and also unrealistic, right? Like if your data is crappy, why would you expect that the model is gonna get it right?
Yeah,
Does that make sense?
that was clear. Yeah, thank you.
And then one other thing to think about, there is a type of model that is actually just trained to detect um, outliers. That is, for example, think about like detecting fraudulent transactions in the bank, for example. There is specific architectures that they're actually trained on identifying outliers, and these are designed in a in like a very different and specific way because the primary goal of these models is to detect outliers. Same for the very common example you'd see in machine learning books like the spam email. How do you label an email as like a proper email or like a spam email? Same for like medical diagnosis, for example. And this is like beyond this discussion, but then this gets you into like as you train a classifier, you get into the difference between precision, recall, and there's something called the F1 score. You can kind of look these up. I was going to include some of these today, but I thought it was just going to be too much. But just saying, generally, you would do your cleanup of the data before. If you have a very specific use case where you actually identify outliers, then these are going to be in your training data and obviously need to be in your test and your validation data. If you're training a model where outliers are going to hurt your performance, you don't want to see this neither in training data nor in your test or validation data. Okay?
Okay.
Cool. All right. So let's now run some code. Um, all right. Let me reshare. Okay. Uh, Are we still recording or did it stop? I see. I wasn't paying attention, but I heard a few times it stopped, that it was recording, and I don't know what's happening.
No,
It's
it's running now.
working,
It
working.
still
Still,
recording. Perfect. Okay. Okay, good. Um, so basically, what I'm hoping to do is I'm hoping to show you um how to perform cross validation. So last time when we ran the model, we didn't really split the data into train or test, or we just had like a very simple example of regression, and then there was an example that we didn't run on the iris data set was a classification, but we're gonna use it today. So hopefully you're familiar with it. Um, and then I'm gonna show you different ways of how do we spread the data into a train test. One thing we're not gonna do, so I explained that we divide the data into train, validation, and test sets. When we're dealing with, simpler data sets like the one we do, we don't really need a validation set. We also are not gonna update any parameters of the models because you're gonna see that they all like work really well. So we don't really need to do this cycle. But then I gave you a small assignment at the end of this thing I said, try and divide or split the data yourself using what the same methods and packages that we're going to describe into train, dev, and test sets and see if you can get it to work this way. And then if you could hopefully take the train def test or just a train test and apply this to the regression problem we applied earlier. This is just hopefully that you get your hands dirty with some code. You maybe just try to project some of the stuff we learn on some real world problems. You could use this with the same data, or you could go on like something like Kaggle and find some interesting data sets to work on. Hopefully the code in here is a good starting point for you to build some networks and play with it and just explore things. And it should be fairly quick to run, but it depends on the data set that you pick. So like I'm hoping that this doesn't become that you're just watching me run the code, because otherwise this is really not going to stick. The only way you're going to learn how to do this is if you just, open up a notebook and you start to write some code yourself and experiment with, what happens if I change this? What happens when I, run it this way? What happens when I split it this way? And you try different things, and then you will see how things behave, and then you're kind of start to get a sense of how these things work. Again, I think I said this before, but one more time, let's say it. There is a lot of stuff that we learn from deep learning that is very empirical, meaning that theoretically some things sometimes don't even make sense, or I mean, I don't want to say they don't make sense. They work, but we don't really know why they work. This is where like a lot of experimentation happen in terms of let's try to do it this way and see what happens. Let's try to change this and see if the model learns better or worse. So I encourage everyone to hopefully use this opportunity to try and apply some of this and then get a sense of how things work themselves. Okay. So this is just me importing libraries, and now we're loading the iris data set. It comes preloaded in the Seaborn library, so I just use it to get access to it. The iris data set in the previous notebook here that we didn't run last time, this is basically, yeah. What is what is the name of the? Oh, I am using Cursor, but this is I think it's a fork of VS Code. But you could also use Google Colab or Jupyter Notebooks or anything basically that opens notebooks. So there's a ton of things, like a ton of ways you can run this. And then I think last time I also gave some instructions on how you set up your environment and install your packages and whatnot. Hopefully it's pretty straightforward. Yeah, Muhammad, you have a question?
السلام عليكم.
عليكم السلام ورحمة الله.
حضرتك بس أنا كان عندي سؤال، هل في الديب ليرنينج إن نبدأ بباي تورش أحسن ولا تنسر فلو؟ أيهما أسهل وأيهما أكثر استخداما حاليا يعني؟
I think PyTorch is much more widely used right now. There's still things I like to use from TensorFlow. Like if you're training a model, for example, they have nice visualizations where you can keep track of the models. Again, these are for models that take days or weeks to train. So you just keep track of the loss and how things are progressing. And if you need to make changes and stop training, you do it. Um, PyTorch has been very popular lately because of the simplicity of the platform and how you can do things with very few lines of code. Um, TensorFlow could sometimes give you more customization, if you will. I mean, maybe that's not fair to say to PyTorch, but yeah, I mean, TensorFlow could give you maybe a little bit more control of some of the things. Maybe PyTorch can tend to abstract away some of the things. Sometimes there are user exposed arguments that you can change them, but sometimes it is how it is. And if you need to change something, you would probably just like do a custom class or something like this. But these are kind of technical things. And it's not something that I would worry too much about as I'm starting to learn this. So the short answer to your question, stick for PyTorch as you're learning this. If you come to a point where you think that PyTorch is limiting you or there's stuff you need to do that is not easily done in PyTorch, by all means go and use TensorFlow. But at the end of the day, these are all, tools and you can use whatever you're more comfortable with. But I wouldn't distract myself too much as I'm learning with, oh, should I go with this or that? It's the same idea that people ask me if I'm trying to learn how to analyze data and data analysis and stuff, do I use R or Python? It doesn't really matter. You're just learning. Learn one of the two. You're gonna have one extra toolbox to use. Whether that's R or Python, it's not a bad thing. Both are gonna do you well. And then when you go to a place where you actually understand how it works, it's gonna be much easier than to learn the other language. Okay?
Okay, thank you.
Um, yeah, so the iris data set is basically a data frame where you have four different features. These are the sepal length, width, and the petal length and width. And then you have a label, which is the species. So these are different flower species, three actually, and every one has four different features. And then basically what I'm showing you here is how these features kind of correlate or overlap with one another. So you can kind of see that, for example, if you would like to classify or you'd like to like using one step back. The goal here is to use these features. If I give you these features, like if I give you the sepal length width and the petal length width of a certain flower, can you expect or can you classify the species of that flower given these features? And so one of the things you would do is you would first plot the relationship between these features. So you would see like, for example, this species here seem to, separate on the sepal length and what's this? The sepal width. So if you use the sepal length and the sepal width, you could, fairly easy separate the setosa from the versicolor and virginica. But you can kind of see here that the versicolor and virginica are kind of clustering together in the same cluster, so it's not very straightforward to separate them. And you can kind of go and explore the features yourself. And if you, for example, find that one feature is separating them well, so maybe you can use these to make the classifier. But the idea is, hopefully, that what you will see here is that there is no combination of features here that is going to give you a very clean separation of all the species. So you need to train a classifier model to learn some patterns um, given all the features together, the four features together. So back to here. Um, what we're doing basically here is you've seen the data. So we are using the first four columns of the data, which are the features, the four features. And this will be our training data, right? Because the input of the model are the features. And then the output are the labels, which is the last column of the data. Okay? And here, instead of having the features being called by their names, Setosa and what was the other? Virginica and versicolor, we're just gonna encode them as 0, 1, and 2. So we're starting like a tensor that is all zeros, and then if it's a versicolor, we're gonna call it 1. If it's a Virginica, we're gonna call it 2. So we haven't really done anything here. We just separated the data from the labels, and then we turned the labels from names into numbers. Now, this is where we split that into training and test data. This is a very simple approach. If you have a very simple data set, we're just going to use NumPy. So NumPy is basically, hopefully you know what NumPy is. It's a library for like mathematical calculations, very, very popular very popular in Python, very fast as well. So what you're doing here is you're basically deciding what proportion of training out of the data you want to use, right? So for here, I said it's a proportion that is like 80%. So I would like to use 80% of the data set as training data. So I take the length of the labels, which is the length of the entire data set, and I multiply this by this proportion that I set up here, and this gives me the number of the training examples that I'm going to use. And then I'm going to create a Boolean mask, which is a mask of trues and false, so that I could use it to subset the data into test and into train and test. Again, I'm going to set up this into the same length as my data set, and I'm going to set it to zeros. And I'm going to set the type to Boolean so that it's only trues and falses. And then
Sorry, I
here,
don't understand that line.
which one? This?
Yes.
So I'm instantiating a Boolean vector with the same length of the data, and I'm setting the type into a Boolean, so true and false. The idea here is to basically, do you know how a masking vector works? So for instance, if I would like to subset my data, I can pass a Boolean mask to it. If the values are true, it's going to pull some indices, and if the values are false, it's going to just leave them behind. This is kind of basic Python.
Yes, I understand. I understand what does it do, but what actually does, I don't know.
What it does, as in like what this line does?
Yes.
So we can do this. We can do this. We can comment. Oops. We can comment this out, and then we can run this, and this is what you get. Basically, this train test Boolean is a vector of zeros that has a length of the same length of the labels, which if you count these are going to be 150 because this is how many examples we have. And we set the type into Boolean. And in Boolean, it's true or false, which is also zeros and ones. So if something is zero, it's a false. If it's one, it's true. So we are basically creating this vector here, or like this array, NumPy array. Does it make sense or still not?
I understand the syntax, but I don't know what it does for real.
This is what it does. The next step is then going to show you how we're going to use it.
Okay.
So then what we do next is out of these, we're basically picking some random indices to the same length of the end training vector here. So the end training, we define this as 80% of our data. And then we're picking some random variables from these, from some random indices from these, and storing these as like a training index. And the indices of this inside this train test Boolean, we're going to set this to true. So now if we run this, it's going to look like this. Remember, before running this 2 lines, when we had these commented out, everything here was false because we've initialized this as a 0 vector. So zeros are falses. Now we're picking some random indices, and these random indices then we're going to set them to true. So now we have this mask here where we have 80% of it is true and the remaining 20% is false. Does it make sense to you?
Okay, the training will take the true and the test will take the false.
Yes, exactly. So then once you pass this mask array to the training data itself, it's gonna select the values that are true and it's gonna leave the values that are false. So now then everything that is true is gonna be your training set, which is like 80% of your data, and everything else is gonna be false, so it's gonna be part of the test data. And then we could test how well balanced this is. So like, re remember here, this is the utility of converting this into numbers. Remember here, we instead of using the names of the classes, we converted these to zeros, ones, and twos, right? And then if we have an equal distribution of all these pieces in our training and test data, the mean of them should be one, right? So like if you have the three classes, 0, 1, and 2, if you take an average of them and there is equal proportions of every one of them, the mean should be 1, which is clear when we apply this. We're just taking the mean of all the labels. You see that the mean is actually 1. The training data is slightly less than 1, which means we have more of the class 0 and less of the class 2, right? Mathematically, this is how it would work. You have more values of zeros and less values of 2, so the mean is less than 1. And the test set is the opposite. Obviously, because there's more zeros in the training, then what's left out of the data is more of the 2s. So you see that the mean is more 1. And then because this is random, you can kind of repeat this process of selecting like random NDCs and repeating this until you get values that are better. So for example, this is now the opposite. Now you have more twos in the training data and less twos in the test data. You could keep doing this until you have equal proportions. Yeah, so this is better, for example. This is like 0.98 and this is 1.06. And the reason why it changes every time is this function here is just making random choices of the indices and then assigning some of them to true and some of them to false. Does that make sense? Hopefully that's clear. This is quite simple. What we're trying to do here basically is to guarantee that our split of the test and training data is equally representative of the three different classes of the flowers. Okay? And then this is exactly the same code as last time. I'm just wrapping this into a function. So we're using the torch and then sequential. We're defining the input layer. Obviously, we have 4 features, so there has to be 4 features. And then we're choosing the hidden layer dimension to be 64. And then we're passing this to a ReLU function. Then that's the second hidden layer, which takes as an input 64, which is the same output of the hidden layer. These have to be the same number. And then it's also outputting 64 layers. And now this is the output layer, which is 64. So it takes an input, the output of the previous hidden layer. And then it obviously outputs, it obviously outputs 3 layers, 3 outputs because we have 3 classes. So we'd like to predict a probability for each one of those classes. And this was from last time, which we didn't discuss. We are using a loss function called cross entropy loss. So cross entropy is basically, I wrote like a little blurb on it in the previous notebook. It's basically a surprise factor. So the way you calculate it is you take minus log the probability, the predicted probability, and this number, then if this number is, if the true label is 1, it uses minus log the predicted probability. If it's 0, then it uses sorry, this is where when it's binary, it just takes minus log the probability of the correct class. So then if it's if the probability is close to 1, meaning that the probability of the correct class is close to 1, this is going to be a big number. And if the probability is of the correct class is close to 0, then this is going to be, oh, sorry, the other way around. This is going to be, as the probability gets closer to 0, then the minus log is going to be close to the infinity. So the loss is going to be really big. So if you're predicting, or if you're selecting, if you're assigning the probability of the wrong class, or if the probability of the correct class is really low, then the loss is going to be really high. Sorry, that was confusing. Let me say that again. If the probability of the correct class is a low number, meaning that the model is not predicting this well, because if the probability of the correct class should be high, should be the highest probability, meaning that the model is learning how to classify the model. So if this number is low, meaning the model is wrong, then the minus log of a small number, which is close to 0, is going to be a really, really big number. Okay? And vice versa. So that's what we're using here. And cross entropy is like the most commonly used loss function in the classification problems. Um, so we define the model, and then we pick the optimizer, the stochastic gradient descent, which we described last time, and then we put through it the parameters of the model that are defined here, and then we return the model and the loss function, the optimizer. So now this actually just defines the function, and this when we run this, it does create the function to us. And now we can check, the sizes of the data that we have. So our data this is the entire data. This is the 150 examples. This is the entire data set. And it has 4 features, which we just described. And now if we would like to know what the training set is, which is, we define this as 80%. So 80% of 150 is 120. And then the test data set is 30 examples. And you see here, this is the utility of the train test Boolean that we created. So once we pass, so this is our data. Once we pass this mask to it, it essentially filters out everything that was false and keeps everything that was true. And in here, we're just negating that mask. So it's basically, it's saying, take everything that was supposed to be true here and just reverse it. So now it's kind of flipping the true and falses so that it's returning the test data set. Does that make sense?
Yes, one for the train and the other for the test.
Yes. And now this is the classic loop that we ran last time. We define the number of epochs. We initialize the losses all to be zeros, and then we just create like an empty list to store the losses as we learn. Y hat is like our output of the model. So we pass here. This is the different part. So last time we passed the data because we weren't really doing training or test data. We can also save this into a variable. So like we can come here and say x equals data, and we just use the mask to extract the x data or call this x train or something. Oops, x train. And then we can also define a y train, which would be the labels filtered with using the same mask. So remember when we loaded the data, we put the data features, the first 4 column into the data, and then the actual labels or the Y output values, we stored them in labels. So this is our Y, this is our ground truth Y, we call it labels, and our input data is called data. So this is what we're doing here. Or did I go? Yes, this is what we're doing here. We're passing y hat. We're passing the training data to y hat. Then we compute the accuracy, and then yeah, this is a little bit. Like you could basically calculate the loss and then append this here. I don't know what I did it this way, but the idea is we're trying to with every epoch, we're trying to save the loss so that we can visualize it later. Then we compute the loss, which is basically the difference between the y hat we calculated here and the labels. But remember that the labels, again, has to be subsetted using the same Boolean mask. So that we're only comparing, because the y hat here is computing the values for only the training data. And we also want to compute the difference between the y hat and the labels in the training data as well. Then after the loss, we calculate the backpropagation using the same functions as last time. We set the gradients to 0, and then we do the backpropagation using the dot backward method, and then we update the weights using the step method. We went over this last time. Okay? And then in here, then we're basically computing we're doing one final forward pass using the training data. So again, in here, we're just evaluating the accuracy on the training data itself. And then in here, we're evaluating the data using the test data. So now we're just using the model. Now the model has the updated weights and biases that we learned in this loop. Now we just do a feed forward using the training data, and then we define the training accuracy here. And then we just print them here. So you see that the final training accuracy is like 98%, and in the final test accuracy is 93%. So not bad. When you run this multiple times, because this is a small data set, you can get into examples where the test is actually higher than the training. This is not really a situation where you will see a lot in real world, but because this is a minute training data of like 150 examples, you can see some kind of unorthodox things like this. But by and large, you will see like with like minimum training and not very complex models, you will see that your accuracy is usually close to 100% most of the time. And if you run this multiple times, you're obviously gonna get like different numbers because there is the random picking of examples from the training and the test splits. There is the randomness in initializing the model weights and biases that sometimes converge, sometimes they converge well, sometimes they don't converge as well. And I think we've seen a lot of examples last time on how can like the nonlinear function. We saw the example where like the ReLU produced like the dying ReLU phenomenon, and we solved this by changing this to rectified ReLU and whatnot. The addition here is that now we have the training and the test data sets. So in this model has not seen the test data set except in that step. So the test data set did not go into the training. The models has not have the parameters of the models have not been updated by using the test data set. It was only the trained data set. And now we're only using the test data set just to use that model to compute the forward pass. Okay? Sorry, I'm trying to talk a little fast because we're running out of time and I'm trying to get through this. All right. Let me just do this using scikit-learn. Oh, that's good. Let's make this markdown. So now we're gonna do exactly the same thing, but we're gonna use a library called scikit-learn to split the data into train and test. So this time, we used NumPy to build like a Boolean mask and do like some random split between train and test. And obviously, as you can imagine, once the data gets a little bit bigger and you have more classes and you try to balance your classes a lot better. So we ran it like a few times to ensure that the random indices that are being picked are actually truly balancing all the classes in the training data. If you have, data sets with like millions of entries and hundreds of classes, NumPy almost, guaranteed to never give you like some balanced representation of training and training and testing data sets. So this is where using something like scikit-learn has a really nice function, train to split, and this is like a gold staple in like training all the classic machine learning models. Any book on like machine learning you will find that the train test split is one of the very early functions that they cover because it's a very widely used and it's very crucial to training models that you know how to split them properly into train and test. And there's a lot of functions a lot of options and arguments that you can pass to this function. Like if you just check the documentation of it, there is ton of things that you can do. You can choose to shuffle the data. So for this, for example, we don't really need to pick like random indices and make sure that the shuffling is done properly. It can shuffle the stuff on its own. It can stratify the data. So for example, if you have unbalanced classes, like this data set is pretty simple. We have equal examples of every one of the species. But for example, if you have a data set that is very biased towards, you have 100 examples of species one, but only 10 examples of species two, you would still want to have some weighing on the training and the test so that you have equal representation or you have meaningful representation of every class in your data. If you just pick random numbers and you have like one class that has very few examples, they might not be in the training data or they might not be in the test data. So you don't get to train on them or to evaluate them. So this gives you like the stratify argument, for example, gives you a way to control for the imbalances in the weights of the classes in your data, for example. So there's a lot of things. I think this is one of the very commonly used functions, and it remains, I think, a very good a very good tool to use in machine learning examples and also in deep learning. So the idea here is we're doing exactly the same thing. We're just defining a train model. So everything that we've done previously, we're just wrapping this into a function where it takes an X train and computes the Y hat, and then it takes the Y hat, compares this to the Y train, and computes the loss. Then it does it does the back propagation. So does the zero gradient, the backward, and the step, and then this is where just computing the accuracy of the training at every epoch basically. So I'm just wrapping this into a function so that it becomes a one-liner to run rather than having to repeat the same code again. And now we're using the exact same model. So the same function we built before to create a model, we're just calling this function now. So we're starting a new model, a fresh model. And then instead of, again, repeating this code, I'm just here training the model using the function here. Now, this is the new bit that you haven't seen before. So remember all the code that we've written on NumPy to split the data into train and test and whatnot. Now this is all like summarized in this train test split function. So what you're basically doing here is this train test function is taking basically two first arguments. One is your data, which is the features of the data that we defined, like from the iris data. And the other is the labels, which is the vector of the labels that has the different species encoded as 0, 1, and 2. And then it's taking an argument that is like a train size. And the train size, I'm passing this train proportion here, which is like the same one that I used before, which is like 0.8. There's also like a test size. So if you don't want to specify the train size for whatever reason, if it's easier, you can just say test size and specify this to be 20% or 10% or whatever. So you can just do it however you want to. And this outputs four things, as you can see here. It outputs the vector of train, the X vector of training itself, and so the features, the training features, and then the test features, and then the training labels, and then the test labels. And you see that this is a much more concise version than using the NumPy method. And it does everything that we did and even better because it gives you options to stratify the different labels and whatnot. And so if you run this, this is essentially similar to what we did in the entire notebook, all the cells before this. And then you can visualize this. You can see that this is how, because here we're recording the accuracy, the accuracy of the training and the loss as the model is training. We can kind of see how this changes. So you see that the training loss is usually less. Sorry, this is the accuracy. This is not the loss. Sorry. So this is like the reverse of the loss. So you can see that the accuracy of the training is slightly higher than the loss, which is what we expect. But eventually, once we get to like 200 epochs, the difference between the train and the test is really, really tiny, which is what you would like to see. You would be more concerned if, for example, your accuracy on the training is like 95 or so percent here, and then your accuracy of the test is like 50% or so. This would mean that you're really overfitting your data, and then you need to go back and make changes to your model. Okay, the last thing I would like to show you today, and this is really, really important, is the PyTorch data loader. So once you get into like bigger models and bigger data sets and stuff like this, really what people use on day-to-day basis, and this is like the kind of production level that you would use, is like the PyTorch data loaders. And what this really does is it gives you an iterable of your data that you could just pass to your training training loop, and it does this in a very nice and easy way. Why this is better than something like scikit-learn is this also gives you the chance to do mini batches. I haven't really talked about mini batches, but this is a way to or like a place to bring it up basically. Everything that we've done so far, we were putting like every epoch, the data was training or the model was training on the entire data set at once, right? So we were putting all the data here. Like with every one of these epochs, we're basically passing the entire training data, the X train, all of the data in the X train to the network and computing the Y hat from all of this, right? The idea of mini batch training is that we're going to take this training data, which is 80% of our data, and break this to even smaller chunks. So maybe a chunks of 10% each. And what this allows us to do is instead of passing the entire data to the network at once, we're going to pass only a subset of the training data. We calculate the loss, we update the weights, and then we go and do this over the next batch of training. This essentially means that instead of updating the weights one time for the entire data sets, for the entire data set, we update the weights depending on the number of batches that we use. So if we have, let's say, 10 batches per epoch. So with every one pass on the data, we update the weights and the biases 10 times, which means that the model is going to learn really, really faster. And the use of the data loader, one of the very powerful uses of the data loader is it very easily allows you to specify a batch size as you're loading the data into the model. So this is like some fake data to show you how the data loader actually works. So data loader comes from the torch utils package. So like the same package that says PyTorch, but remember we were using the NN or neural network. Now this like the data utils module in the PyTorch has the data loader. This is fake data to show you. I found this in one of the popular repos, one of the people teaching deep learning. So it was actually a pretty nice example to use. So basically what they're doing here is they're creating this fake data to show you how the loader can actually handle the data. So the data itself is like these vectors of features. So you have it goes like from 11, 12, 13, 14, and then every time they change the like 20, 30, 40 so that you can kind of easily see it. And then there's like a labels vector, which is very similar to how the data is structured, like the iris data. We have 4 features, and then every feature has its own class or label. So this is exactly what this does here. And then he passes this data into the data loader directly and setting the shuffle to true. Now, so this is like shuffling the data. And then you see like when you print this, it doesn't really print anything because this is an iterable, meaning that this is like something that you need to iterate through so that you can kind of expose the stuff inside. So in order for you to actually see the data inside, you would use something like an enumerate function. And now like with the data loader, you pass this into the enumerate, and then you can kind of see like what's inside of it. And you see like because this is random, you see that, for example, the first example here is shuffling like now this was like the last row here. So now it became like the first one here because we're setting shuffle to true. If this was set to false, then you would see exactly the same order here. You see now it's like the same order as the data before, right? Sorry, that's here. The same order as the data before. So we were going to set this to true because this is how you want to do it. And then you do this, and now it's like back to being shuffled again. Okay, so there's one more thing to do. Now, you see when we created this data loader, this is only the data itself. We don't really include the labels here. So where do the labels go? How does the model, like when the model creates computes the y hat, where are the labels that it's going to use to compute the loss? In order for us to do like proper data and labels, we have to create something called the tensor dataset. And again, the tensor dataset is another thing that you can import from the torch utils data. So actually, we could, instead of doing this way, we could just in here import the tensor dataset. And then we don't really have to write it this way. Here we just use it like this. So what this basically does is using that same fake data object that we created. Now the data set passes the data and the labels, and then now it creates this tensor data set that you can then pass to the data loader. And the data loader automatically uses the first entry here as the data and the second entry as the label. So now once we do this, now you have two things here. So once you cycle through the items in the data loader, you have first your training example. Sorry, we're printing what? Yeah, so sorry, we don't really need to print this. Yeah, there we go. That's what we need. So once you create the tensor data set here, and you pass this to the data loader, once you cycle through the items in the data loader, you can see that now it's printing you the data itself together with the label associated with it. Obviously, the labels were trues and falses, and now they're printing as zeros and ones because these are tensors. Okay, is that clear?
Can we repeat this part next session? The beginning of the next session, because I can't
Okay.
I can't take
Okay.
it.
Okay, we can go over it one more time because it's actually pretty important and you need to understand how data loaders work and how to create one yourself. I'm just gonna finish this, but we're gonna go over it next time. So what we basically do here is we're gonna use train test split the same way that we used it previously, and we're gonna ask it to what is it called? Split the fake data and the fake labels into train and test. Like this is the exact same line that we ran before. We're just running this on the fake data, and it's gonna give us the same four items that it produced before. So we have the training data, the test data, the training labels, and the test data labels, which you called previously X and Y. So it's the same thing. And now because you have your training data, now we can create a tensor data set from the train data and the train labels, right? So this is exactly the same code that we use here, but now we're creating different train and data, different train and test objects. The train is going to be the train data and the train labels. The test is going to be the test data and the test labels. And now we're basically creating a data loader. Here, this is the bit that I wanted to show you. We're specifying the batch size equals 4, meaning that we're going to create a batches and each batch is going to have 4 training examples. So when we go and print this, you see how this now looks different. So remember when we printed this previously, everything was just in the same, like you have like a single example of being one training data example and its label. In here, we have like a tensor that has 4 examples, including the 4 rows of the data, plus their 4 labels. So this now becomes a batch. Okay? So now if we apply this on the training data, I'm not gonna go through the code now because we're gonna do it next time. Now you have like we split our we defined the batch size to being 12. So we split our training data now to different batches of 12 examples per batch. And what I want to show you now is once we train this, you see how quick this model learns. So we see like in like 50 maybe epochs, you see that both the like we've ran this to 500 epochs, but essentially by the time we reach like maybe even less than 50 epochs, the model has learned. If you would like to see how this compares without batches, we can go back to here and we, instead of setting the batch size to 12, we can just use the train data and set it and use the train data. Basically, you have as many batches as the train data. So once we run this, you see now it looks very different. Now everything is in the same batch. So we have a single batch. It's the same dimension of the training data, which is 120 by 4. So all the training data, all the labels, and now this is already defined. We just create the model and prod the results. Now you see how much slower training is. Remember last time it was like 50 and like the train and the test both were almost at 100% accuracy. This took about 100 epochs to actually get like decent accuracy. And obviously this is a tiny data set. So if you're doing this with a data set that has millions and hundreds of examples, well, first of all, loading the entire data to training becomes resource limitation because you need memory, you need RAM for this. So it's not practical. The second is it's going to take you way too long for the model to learn something if you're only updating the model, the weights and biases one single time per epoch. So you see that once we did the batch sizes to like batches of 12, the model was learning, like if I go back to 12 here, and I run this, if I run the model again one more time, it's going to be really, really much quicker. Hopefully that's, I mean, the data loader part, we did it like really quick. I apologize. But we're going to go over it one more time next time. Any last minute questions?
Yes, what if we want to add a validation set while using train test split function?
That's your assignment to do.
Okay.
There is nothing you need to like. Like the answer is within exactly the same code. Think about how this code works, and think about how you want to do this. You can do it using NumPy. You can do it using the train test split from scikit-learn. These are the only two. By the way, the data loader doesn't split the data. The data loader, you only use it to build the iterable that you're going to pass into the model, but it doesn't really split the data for you. Like if you go back to the code, we are splitting the data using the train test split, and then using the splits that's created by this function, we're building the training and the test data using the data loader. So there's only two ways that we've discussed really. The way of doing this manually using NumPy, which is you can do for fun just to understand how things are, but in practice, this is not really used. Train test split is very decent. It gives you a lot of options. And if you would like to do this, if you would like to split the data into train, dev, and test, you can do this, I guarantee, with the same functions. You just have to think about how you want to do this. Okay? Don't go to ChatGPT and ask it right away. Try to think about it, please.
I think we can get a subset of the test or something like that.
You do your thing. Next time, let me know how you did it. You can also put on like Discord if you managed to do it. You just like take a screenshot and put it. Or you can send it to me so that people also try it on their own. Like don't burn the solution for everyone. So yeah. I mean, this is a fun thing to do, or yeah, just don't really take it to ChatGPT right away and ask it to solve it for you. Just try to think about it a little bit. It's like it's really simple, and I guarantee the solution is within that notebook. So you don't really need to read more documentation or think about like an argument that you didn't know of the function. It's exactly using what is there. Just think about the problem differently. Okay? All right. I think we're out of time. If no more questions, we can wrap it up here. And next week, I have a conference on Monday. So that would be like one day after the session. So I'm hoping I can make it. But if things get out of hand in preparing for the conference, we might have to skip. I apologize. But I will do my best to try and be here. But just heads up. Shah, do you have a question?
أنا سؤالي عن البرنامج وحضرتك رديت، بس قصدي زي مثلا اللي أنا أشتغل عليه، حاسة إن البراوزر غريب عني. يعني اشتغلت قبل كده على ار ستوديو، يعني مش زي كده، وبرضه قبل كده اشتغلت على بايثون، بس حاسة إن ده براوزر غريب عني. فممكن لو في اتفضل.
لا يعني you can use when you انت بتقولي اشتغلتي على Python, what did you use when you like not what is it
كنت
called?
كنت شغالة على فيجوال ستوديو.
هو VS Code, you can use VS Code. Yeah. This is
تمام.
this is exactly this is a fork of VS Code. This is Cursor, just has built-in AI and stuff. You see like the autocomplete and stuff as I'm working. But so
تمام.
يعني this is very similar to VS Code. There's also like the classic ones, what are they called? The other like Python IDEs. Like this is basically like a personal preference to you. Like everyone picks their own IDE that they like to use, and it's a personal preference. There's no right and wrong. whatever is more comfortable to you, just use it.
تمام، شكرا لحضرتك.
Any more questions? All right. أشوفكم إن شاء الله على خير المرة الجاية إن شاء الله. السلام عليكم.